In this video, I am going to explain about fundamental theorem of calculus. See, calculus basically has two branches. One is a differential calculus and the other one is your integral calculus. The differential calculus concern with derivatives and integral calculus concern with integrals. I'm writing as I and the derivative I'm writing as t. So what this fundamental theorem does and why it is named so? This theorem is named a fundamental theorem because it plays a central role in unifying calculus. So now before FTC, fundamental theorem of calculus, it was considered that there was no link between D and I. There was no link between D and I. It was considered between D and I there was no link. But after FTC, we came to know the differentiation and integration are inverse operation of each other. Of one another. The next question is why this theorem is essential. Why it is essential? See, the part 1 of this theorem establishes a link between D and I. The link is inverse operation of each other. So that is d by dx integration from a to x ft dt equal to f of x. So what it does here, see, integration is followed by differentiation. So integration is followed by differentiation and bring the function back to itself, brings the function back to itself. And the part 2 of this theorem, what it does actually, it simplifies definite integral. Like say a to b f of x dx equal to uppercase fb minus f of uppercase fa. So where uppercase fx equal to antiderivative of fx. So before FTC, finding definite integral was incredibly difficult. So before FTC, finding definite integral was incredibly difficult. So now what conclusion can you derive out of it? What conclusion can you make out of it? So without FTC, fundamental theorem of calculus, D and I, differentiation and integration, were considered disconnected techniques. But with FTC, it became unified. Now we'll prove the part 1 of the fundamental theorem of calculus. So part 1 of FTC. We're going to prove in detail the part 1 of the fundamental theorem of calculus. So this theorem says d by dx integration a to x ft dt equal to f of x. So now you see integration a to x ft dt is nothing but the area under the curve ft. So first let us draw the curve. So the curve I'm drawing is like this. So this is f of t, and this function is defined and continuous in the interval a to b. So let f of t is a continuous function in the closed interval ab. Now let x be a variable. Say x, this is x variable point. Let x be a variable point in the closed interval ab. Now see, let's say a to x ft dt is equal to uppercase fx. So what this indicates? This indicates the area under the curve ft from t is equal to a to t is equal to x. So that's what it says actually. So I'm like, drawing it by red sketch here, red pin here. You see this is the area from t is equal to a, t is equal to x. So now our aim is to prove what? Our aim is to prove d by dx of uppercase fx equal to f of x. So now how do you prove this? Okay, let me draw the diagram again. So the diagram is like this. This is defined in a to b and x with a variable point. So this area is uppercase f x. Okay. Now what you do actually, take a point sufficiently close to x. Let this point is here x plus h. So take a point sufficiently close to x. So therefore area from t is equal to a to t is equal to x plus h will equal to how much? Integration a to x plus h f of x ft dt. and this it can be written as uppercase F x plus h. So I'm drawing a different pen now. This area I'm talking to you, this area is the blue color, that is equal to capital F x plus h. Now if you subtract say f x plus h minus f of x, what you will get? This you will get the area under the curve from t is equal to x to t is equal to x plus h. I mean this area, I'm drawing it by this area, the pink color. This area is the area from t is equal to x to t is equal to x plus h. Now this area, see now if I draw a rectangle here, let me draw the rectangle like this. This is the inner rectangle, and now this is the outer rectangle. So area of the inner rectangle is less than equal to area under the curve is less than equal to area of outer rectangle. Now see for the inner rectangle, this is your length h, that is, and this is your f of x is the breadth. So area will be h into f of x, that is equal to less than equal to area under the curve is f of x plus h minus f of x is less than equal to outer rectangle area will be how much? See now if you look at the diagram again, this length is h, the breadth here is your f of x plus, the height is f of x plus h. So this is equal to h times f of x plus h. Now what you do actually, will divide throughout by h. So f of x is less than equal to fx plus h minus f of x whole upon h less than equal to f of x plus h. Now you take limit, h tending to 0. So limit h tends to 0, f of x less than equal to limit h tends to 0, f of x plus h minus fx whole upon h less than equal to limit h tends to 0, f of x plus h. Now you see, by first principle we can say this is the derivative by first principle. Okay, so now this is limit h tends to 0, f of x is less than equal to f dash x or f prime x is less than equal to limit h tends to 0, f of x plus h. Now as h is tending to 0, your x plus h will tends to x. So this we can write as f of x less than equal to f dash x and less than equal to f of x. Therefore, by squeeze theorem, we can write f dash x equal to f of x. So this is d by dx of fx is equal to f of x. So d by dx, so fx is we have taken a to x, ft dt is equal to f of x. Now hence it is proved. So the next video I am going to solve problems based on fundamental theorem of calculus. Thank you for watching this video.